In this video, we're going to be going over kernel, or kernels. This is often called null space. And essentially what a kernel is, let's say we have some linear transformation T, and let's have it be some transformation from Rm to Rn. So what this means is it's going to be given by an n by m matrix, right? The kernel, so now that we have this transformation, the kernel of this transformation is the set of all vectors in Rm so this first space Rm that such that the transformation of V equals the zero vector. So it goes to 0. So kind of what an illustration of this would look like. So we'd have two spaces. So we'd have R M, then we'd have R Rn over here. And then there's a zero vector here in Rn. And there would be some space here. It could be just one point, or it could be a bunch of points. So in this case, it looks like it's a bunch of points that all map to this zero vector. This space, so this is the kernel. So this thing is the kernel right here. All of these vectors map to the zero vector. So great, now we know what the kernel is. Let's have an example. So, example. Let's say we had this matrix over here. Just let's call it A equals. So I'm going to have this already be in reduced echelon form. So let's call it 0, 3, 1. Let's call this -1. Then 0, 1, -2, 1, and then just all zeros on the bottom. So this is the matrix for some linear transformation. To find the kernel of A, I would just set this all equal to 0. So the reason again that we're setting this all equal to 0 is that we want all the vectors in Rm that go to 0, that have the solution of 0 in this new space Rn. And what this vector that we have, or this matrix here, is doing is it's a transformation. When we apply the transformation, we're going from Rm to Rn. So this is really key. So now that we've set up this augmented matrix, what can we do? We can now we notice that we have these two free variables over here. So these are free variables. And the reason that they're free variables is because they don't have a leading one. So these ones are often called pivots, or just rows with leading ones. These variables don't have leading ones. So we can now write this stuff out. So we can say, we can label this, we can call this x1, this is x2, this is x3, and this is x4 over here. So we can say x1 is equal to negative 3 x3 plus x4. x2 is equal to 2 x3 minus x4. And then since x3 and x4 are just free variables, we can just set them equal to themselves. So now that we have this system right here, we can show the vectors that would create this kernel. So we can write this as one vector, and we can say it's negative x to negative 3x3 plus x4, and then we can have 2x3 minus x4. We can have x3, and then we can have x4. But we can also write this in terms of both of our free variables. So this can go, let's change the color to that yellow. So we can have x3 times negative 3, 2, 1, 0. And what I'm doing here is I'm just taking all of the terms that have an x3. So this 3, and then there's no x3s here, so I just put a 0. And then we can add the x4, which will just be 1, negative 1, 0, 1. And there we have it. So these two vectors span the kernel of A. So what that means is that if we go back to this diagram over here, these two vectors are creating this space of all the vectors that go to this point over here, which is the 0 vector. So we can create all of the vectors in our null space with a linear combination of these two vectors here. And that's the kernel.